everybody, welcome to this next video. In the last some videos we were talking about what are the derivatives of vector functions and what how we can find the partial derivatives. So in this video we are going to practice some problems, and these problems are based on the fact that with the vector functions we can define the position vector of a particle moving along a curve, right? So we are going to have a look at that how the position vector and acceleration and velocity, they are connected, right? So look at this first problem. Here it is saying a particle moves so that the position vector is given by r is equal to cos of omega t sine of omega t are the ith and jth components, where omega is a constant. Then we have to show that velocity vector v of the particle is perpendicular to r. So first of all, we should use the knowledge that if you are given the position vector of the particle, so you are given the position vector of the particle cos of omega t I cap plus sine of omega t j cap, then how do you compute the velocity vector? How do you compute the velocity vector? For that, you have to differentiate with respect to time. So what you are going to do here is dr by dt, and that will be going to be minus omega sine of omega t I cap plus omega cos of omega t j cap. This is our velocity vector. And then they are asking us to prove that velocity vector is perpendicular to r vector. So how can we prove that two vectors are perpendicular? Now the next question that comes to your mind should be, how can we prove that two vectors are perpendicular? So I hope you all know the answer. So we have to prove that perpendicular, that their dot product is 0. So now if you take the dot, this is your velocity vector, call it v vector. So if we look at the dot product of r and v vector, so your r vector is cos of omega t I cap plus sine of omega t j cap, and then dot product with v vector, which is omega minus omega sine of omega t I cap plus omega cos of omega t j cap. And we know that how to take the dot product. We multiply the ith components, this and this here. So we'll get minus omega sine of omega t cos of omega t. Then you multiply the jth components. So we'll get here plus omega sine of omega t cos of omega t. So both of these are same and with different signs, so we get a 0. So we get r dot v is 0. Therefore, r and v are perpendicular vectors. So that is the first thing we proved, right? And now look at part B. It says that we have to prove that acceleration is directed towards origin and has a magnitude which is proportional to the distance from origin. So how do we calculate acceleration? For acceleration, we must have d2r by dt2. We already computed dr by dt here. So from here, if you compute the double derivative, you will get, this would be minus omega square cos of omega t I cap minus omega square sine of omega t j cap. So that means the acceleration vector, let us call it as a vector, is going to be minus omega square is common. So you have cos of omega t I cap plus sine of omega t j cap. Now that would give us acceleration is equal to minus omega square. If you look at this, what is this? This is nothing but r vector. So we get that a vector equal to minus omega square r vector, right? What does this mean, right? It means that now you know what is r vector. If your particle is moving along any curve, then this vector is r vector. This is r vector, right? So here you can see that you have a negative sign and r vector. That means minus r vector is like this. This is r vector and this is minus r vector, and this is origin. So that means the force, the acceleration is towards the origin. That makes sense? We had to prove that acceleration is directed towards the origin. Okay, so here you can see that, you can say that since acceleration has a direction of minus r vector, therefore it is directed towards origin, because by default r vector is like this, directed towards origin. Okay, so this is how we prove the second part of the problem. Now you look at the last part of the problem. You have to prove that r cross v is a constant vector. So this is very simple. So what you can do is r cross v, how do you compute it? So we know that this is how we compute the vector product. We write the unit vectors, then the components of the first vector, that is cos of omega t, sine of omega t, and 0 here, and here it is the derivative minus omega sine of omega t, omega cos of omega t, and then 0 vector here. And now when you compute it, like we do the cofactors, so what we are going to get is, you are going to get only k vector times, you multiply these two and these two, you'll get omega square cos square omega t plus omega square sine square omega t. So that would be k vector with omega square. Therefore r cross v is omega square times k vector, which is a constant vector, you can see. Right, so this is I'm sorry, this is not omega square, this is omega, right? Okay, yeah, okay. So this is the mathematical part of the question. But if you look at the question again, if you try to see what physically this thing is denoting, then you would come to know that, you see, look at the position vector. This cos omega t and sine omega t. This is a parametric equation for a circle with radius equal to 1. Right? So it is the motion of the particle along a circle, and we know that when particle moves in a circle, the force is directed towards origin, that is called a centripetal force, and we know that the velocity is tangent, and we know that tangent at a point is perpendicular to radius. That is why r and v are perpendicular vectors, and also r cross v is nothing but your angular velocity, right, which is omega in this case. So you can see that there is a connection between what you have studied in physics, right? You know that actually when you have a particle moving along a circle, right, the radius vector and the velocity vector, they are perpendicular, and then the r cross v, which gives us the angular velocity, that is also constant, right? Okay, so that's good. Now look at the next problem. These problems are just to give you an idea of what kind of problems you can face when you are dealing with vector calculus. Okay, so practice makes a man perfect, right? So you have to practice, practice and practice. So let us read this question. Let A has a constant magnitude. Show that A dot dA by dt is 0, right? So what we are going to do here is, A has a constant magnitude, so I have mod of A equal to constant, right? So I don't know what to do with modulus, but what I can do is, if I take square, that is also a constant, because if something is constant, its square is also constant. Now you know that I can write it as that A dot A. A dot A is nothing but mod of A square is constant. That thing I got. So now if I differentiate with respect to t, so what you will get, dy by dt of A dot A, that is going to be dy by dt of a constant quantity, and that is equal to 0. So this would be Now if you apply the rule here, product rule, so this will be A dA by dt plus dA by dt times A vector equal to 0. So you get 2 times A vector times dA by dt vector is 0, and that gives you A vector times dA by dt is 0, right? So that is the first part we want to prove. And then you want to prove that A and dA by dt are perpendicular provided dA by dt is non-zero. So we already got that A dot dA by dt is 0. So we know that the scalar product, which is the dot product, is 0 only when the vectors are perpendicular or one of them is 0, okay, or both are 0. So here for sure A has a constant magnitude, so we assume that it is not 0. So they are perpendicular if dA by dt is non-zero, because if dA by dt is non-zero is 0, then we are not sure that the angle between them is 90 degrees, right? But if dA by dt is non-zero, then we are sure that the angle between them is 90 degrees. Okay students, keep watching our videos, share, subscribe, and just happy learning. Bye.